So, today we will continue samarium iodide in organic synthesis. So, first we will discuss functional group transformation, the reduction of alpha heteroatom substituted carbonyl groups with samarium iodide, and here we will discuss reduction of alpha heteroatom substituted ketones, reduction of alpha heteroatom substituted esters, also reduction of alpha heteroatom substituted amides. Also, we will discuss beta elimination reactions by the reduction of alpha beta heteroatom substituted, that we will see generally alpha chloro and beta hydroxy is there, then you can get the beta elimination and alpha beta unsaturated carbonyl compounds you can generate. The reduction of nitrogen containing compounds is samarium iodide, that also you will see nitro compounds. Reduction of sulfoxides and alkyl sulfonate, that also we will see. Then we will discuss carbon-carbon bond forming reactions using samarium iodide. And here we will discuss pinnacle couplings, intramolecular pinnacle couplings, intermolecular pinnacle couplings also, and pinnacle couplings of imines and their equivalents also we will discuss. Then we will discuss carbonyl alkene coupling, this is very important C bond formation. Carbonyl arene coupling also, then reactive couplings of imines and their equivalents, and finally we will discuss radical alkene alkyne additions, generally these are intramolecular, that we will discuss. So, first we will discuss the reduction of alpha heteroatom substituted carbonic compounds with samarium iodide. So, in the case of samarium, last class we have seen when the alpha halo ketones are there, then we have seen that they generate the enolates. So, here also the reduction of alpha heteroatom substituted carbonyl compounds to the parent carbonyl compound is one of the most common uses of samarium iodide. So, here you can generate the enolate, and that enolate if you coincide with a proton source, then you can generate the ketone. Prior to the use of samarium iodide, zinc, chromous ions and dissolving metal reduction had been used for this transformation. Those methods often required acidic condition and extended reaction times, thus limiting the range of functional groups tolerated. So, this is very important. Earlier methods, the functional groups toleration was very less. However, using samarium iodide, a range of heteroatom substituents can be removed efficiently under mild, neutral and electron transfer conditions in the presence of a range of other functional groups. So, this is very important. With samarium iodide, you can do this reaction in presence of other functional groups. So, this is very selective, and this process is very fast, that also we will see. So, if you have a carbonyl compound like R1 ketone, then OR1, then ester and NR2, then it will be amide, and X can be halo, OH, OR, OSC, SONR, N is equal to 0 to NR2. So, different X groups can be liberated. With samarium iodide and proton source, you get the carbonyl compound. So, here the heteroatom is replaced by a proton. Now, what is the mechanism? Two possible mechanisms can be envisaged for this reduction, both involving the formation and protonation of samarium 3 enolates. Alpha haloketones react with samarium iodide to give a ketyl radical. This is very important. Ketyl radical is formed, that is then quenched by the co-solvent. A second reduction then gives carbanion that undergoes beta elimination to produce the enol tautomer of the product ketone. So, this is the mechanism. Here the carbonyl is first, actually we can think. So, carbonyl group is first reduced with samarium iodide to generate the radical anion, and then a proton source comes, then it becomes OH, and again another molecule of samarium iodide makes this radical to anion. So, this is anion is forming, and then this anion makes the enol after liberation of X minus. So, X minus is liberated. So, this is the beta elimination, and this is enol is formed, and this enol is tautomer of course of the carbonyl compound. So, in this mechanism the carbonyl is first reduced and then the elimination of X minus happens and you get the enol and carbonyl compound. There is another possible mechanism, because A stars are not typically reduced by samarium iodide that we have seen earlier. Molander proposed an alternative mechanism for the reduction of alpha haloesters. So, the electron transfer to the alpha substituent generates a radical anion intermediate that undergoes fragmentation to give a radical. So, this is the samarium iodide here giving electron to this X. So, X become now X dot minus, and after elimination of X minus you get a radical. This radical again reacts with samarium iodide to generate the anion here, and anion will be of course the enolate. So, here the enolate is forming enolate, and protonation gives the parent A star. So, after protonation of course H plus comes proton source, you get the A stars. Reduction on X. So, earlier we have seen reduction carbonyl, here reduction on X. X is taking the electron from samarium iodide and becoming X dot minus, and after that elimination of X minus you get a radical, then anion. Anion of course will generate the enolate, and enolate after proton source you get the A star. Now, if you have electron withdrawing substrate, then also this kind of mechanism might operate, because X can coordinate with samarium and this A star is getting activated. Once it is getting activated, then the samarium iodide can react to the carbonyl of the A star and to generate this radical anion, and after that again another samarium iodide comes to generate the anion, and after anion you get the elimination of X minus, you get the enolate, and this after proton source you get this. Now, we will see some examples of reduction of alpha heteroatom substituted ketones with samarium iodide. This is an ketone with a alpha substituent. So, where the substituent can be acetate, OSIMe3, OCOCH2PH, O-tosyl, and only samarium iodide 2 equivalent. Methanol is the proton source here, THF solvent minus 78 degree centigrade. You get 75 to 100% yield of this ketone. Here the X is removed. Also, it is interesting, in this ketone if you see there is a acetate OAC at the alpha and beta there is iodide. Now, if you add only 2 equivalent of samarium iodide and methanol same condition THA minus 78 degree centigrade, you get this. So, here the iodide is untouched. That means, this removal is very fast process, because here the iodide is not removed. So, generally we know that iodide generates a radical, but here the acetoxy removal, that is the carbonyl is activated here. So, carbonyl reduction is very fast, and after that you eliminate the acetate and you get this product in 87% yield. This was published in Journal of Organic Chemistry 1986. Also, epoxide and aziridine can be opened if you have a alpha beta epoxy ketone. So, this is alpha beta epoxy ketone, and after samarium iodide 2 equivalent methanol THA minus 90 degree centigrade, only 5 minutes you get 97% yield of this product. So, this is actually beta hydroxy ketone, and this you can generate by aldol reaction. So, that is why it is called aldol product, because in aldol you have the ketone and formaldehyde. So, here also the similar mechanism, that negative charge is forming here OH or O samarium, we can think this OH, and after that this enol will form. So, epoxide will open and it generate this. So, you get this product. Similarly, if you have a chiral epoxide, so with chiral epoxide also you can get this product, that is the beta hydroxyketone. So, this is chiral epoxide. Here also samarium iodide methanol THF condition minus 90 degree centigrade, you generate this. So, this is also chiral. So, this stereochemistry is retained, stereochemistry retained. So, this is very important that chiral epoxide can also open under this condition. Now, this is aziridine. So, here N-tosyl aziridine is present and with samarium iodide 2.5 equivalent, methanol THF 0 degree centigrade, you get this beta aminoketone. So, these are actually Mannich product, because by Mannich reaction you can generate these compounds. And this work was published in JOC 1999. Now, we will see reduction of alpha heteron substituted S star. So far we have seen ketones, now we will see S stars, and S star, it has been found that if you put HMPA, hexamethyl phosphoramide, then the reaction is much faster. So, this is HMPA, and you can see there is a methoxy group present, and with samarium iodide HMPA, this octyl alcohol, room temperature, you get 73% yield of this product. In this S star, there is no methoxy group. So, this is very important. Also, this one, alpha beta epoxy S star. So, this is alpha beta epoxy S star. So, like ketones, we have seen the S stars can also be opened here. Here, samarium iodide, HMPA, and then DME is added. So, DME is dimethyl ethanolamine. So, this had two roles. One role, it is a proton source of course, and another is that it breaks the samarium S star complex to make free S star. And this reaction is very fast, only 1 minute in room temperature you get beta hydroxy S star by epoxide opening in 62% yield. Also aziridine, here N-Bock aziridine is present and samarium iodide, here HMPA is not required, only DME is enough, 5 equivalent DMAE and THF 0 degree centigrade, you get this beta amino S stars in 82% yield. Also tosyl aziridine can also be opened under similar conditions, samarium iodide 2.5 equivalent, DME 5 equivalent, THF 0 degree centigrade, you get this beta amino tosyl S stars. Now, we will see reduction of alpha hetero atom substituted amides with samarium iodide. Here also the tosyl aziridine with an amide motif can be opened with samarium iodide 2.5 equivalent, DME 5 equivalent, THA minus 25 degree centigrade, you get 86% yield of this beta amino tosyl amides. Here an acetate group is present, and when samarium iodide 4 equivalent lithium chloride here is used 12 equivalent, and under this condition THF room temperature 24 hours you get 60% yield of this product. So, this is very important, the acetate group here is eliminated and you get the unsubstituted amide in 60% yield. This work was published in Tetrahedron 1997. Also, beta elimination reactions by the reduction of alpha hetero substituted carbonyl compounds with samarium iodide is possible, and the reduction of alpha halo beta hydroxy esters and amides with samarium iodide gives alpha beta unsaturated esters and amides with high stereochemical control. So, this is very important. If you have a alpha halo beta hydroxy esters amides, then you can get alpha beta unsaturated ester. or amide. So, here the hydroxy group is eliminated because hydroxy group is activated by samarium 3 and that is why it can be eliminated. So, like this is alpha chloro beta hydroxy ester or amide. Under this condition, samarium iodide beta elimination can happen and you can get this alpha beta unsaturation. For example, here you can see this is R is equal to O80, then it is A star, R is equal to N82, then it is amide, here a alpha chloro beta hydroxy is present, and with samarium iodide 2 equivalent THF condition, you get this. So, alpha beta unsaturated ester or amide, and when R is equal to O80, then you get 93% yield of this product and 98% diastereomeric excess. So, here this cyclohexyl and this ester motif are in the trans. So, this product is trans. Also with amide you can get similar yield as similar diastereomeric excess greater than 98%. So, what is the possibility of this high diastereomeric excess? You can get this half chair form and this chair form actually of this one. This enolate, as you can see, there is a OH is there is a double bond. So, this is cyclohexane kind of intermediate is forming, and this samarium is coordinated with this OH as well as this O minus, and methyl is here, R is here. So, this is in the pseudo equatorial position, and then the elimination of OH minus. So, after OH minus elimination you get this, and this is very much stereoselective. After elimination it gives this trans orientation. This was published in Angiochemy 2000, also Chemistry European Journal 2001. Now, we will discuss reduction of nitrogen containing compounds with samarium iodide. We will discuss reduction of the nitro group with samarium iodide. So, we know primary, secondary or tertiary nitroalkanes could also be reduced using samarium iodide to the corresponding hydroxylamines or amines depending on the amount of reagent used. And the reaction of nitroalkanes and nitroarenes with 4 equivalent of samarium iodide in the presence of methanol and THF gave the corresponding hydroxylamine, whereas the use of 6 equivalent gave the amine. So, we know that nitro group as an useful group in organic chemistry and various reduction methods are well known, and with tin HCl, and like here we can see the samarium iodide can also do this reduction. Like RNO2, if is there nitroalkane, R is equal to alkyl or aryl, and samarium iodide 4 equivalent methanol THF condition, you get this hydroxylamine. On the other hand, if you put 6 equivalent samarium iodide, methanol THF room temperature condition, you get the amine. So, that means hydroxylamine is an intermediate for the formation of amines. This was published in Tetraidal 1991. The mechanism of nitro group reduction by samarium iodide is thought to proceed by a pathway similar to that proposed for the dissolving metal reduction of such substrates. A series of 4 single electron transfers from samarium iodide followed by proton transfer generate a hydroxylamine intermediate that can then be reduced further. So, this is the mechanism. You can see the nitro compound, first samarium comes, you generate this dot O minus, then H plus comes, you get this OH here, again samarium iodide comes, here it becomes O minus, and nitrogen positive charge is vanished here. Now, after elimination of hydroxide. So, this is very important. The hydroxide elimination is common in samarium iodide reaction because the hydroxy is activated by samarium 3, and you get this nitroso compound, And another equivalent samarium iodide, here then you get dot O minus, and this O minus quenched by H plus, and this dot getting negative again, another equivalent of samarium iodide. After proton source you get this. This is the hydroxylamine. So, with 4 equivalent, this is 1, 2, 3, 4, with 4 equivalent you get the hydroxylamine. Now, we will see reduction of sulfoxides and alkene sulfonates. So, this is sulfoxide, like here this is alkyl sulfoxide, 2 N-butyl group is there, and with samarium iodide here you need excess 22 equivalent. THF HMPA condition 20 degree centigrade temperature, just 1 minute you get this sulfide in 99% yield. Also an aromatic group. So, this is aromatic biphenyl is there, sulfoxide with samarium iodide THF HMPA, same condition 20 degree centigrade 1 minute you get 94% yield of this compound. This is also sulfide or thioether. Sulfide or thioether. This was published in Journal of Chemical Society Chemcom 1989. Now, if you have a sulfone, so this is called sulfone, and generally the alkyl alkynyl sulfone. Alkyl alkynyl sulfone, it gets completely eliminated under samarium iodide condition. So, here samarium iodide 5 equivalent HMPA THF minus 20 degree centigrade 90 minutes, 50% yield of this product. So, what happens, most likely a radical is formed, the radical reacts with samarium to generate the anion, and then the proton source come. So, this sulfonyl SO2 pH group completely removed. This is very important, we will see later that this radical is formed that can add to olefin, but here just if you add a proton source, then you can get this removal. And here this vinyl sulfone is there. So, this is alkyl sulfone and this is vinyl sulfone. So, in vinyl sulfone also with samarium iodide 5 equivalent HMPA THF minus 20 degree centigrade 90 minutes, 68% yield of this compound is obtained. This was published in Tetraeden later 1991. Now, we will discuss carbon-carbon bond formation reaction using samarium iodide. So far, we have seen different reaction with the functional groups. Now, we will see that whether we can combine this strategy with CC bond formation reactions. So, first we will discuss pinnacle couplings. Since the discovery of the pinnacle coupling reaction over 150 years ago by Wilhelm Rudolf Wittig, this reaction has become an important synthetic tool for the construction of carbon-carbon bonds. The reductive coupling reaction between two carbonyl compounds represents a valuable alternative to the osmium tetroxide mediated dihydroxylation of alkenes for generating 1,2-diols. So, this is very important, this is an alternative to the osmium tetroxide mediated dihydroxylation. Typically, low valent metals or complexes thereof can promote this reaction, and it is well accepted that metal ketyl radical anions are intermediate in this reaction. So, like that we have seen that carbonyl group reduction, the ketyl radical anion also is forming, and that will generate the pinnacle product. Due to the ease with which the reagent is prepared and used and the characteristically high yields of pinnacleic products, samarium iodide has become one of the most popular reagent for mediating this class of reaction. So, here you can see carbonyl compound is present, and with 2 equivalent you can get either 3O. So, this is 3O product or erythro product, 2 products you can get, and we will see the selectivity later, and samarium iodide only can do this pinnacle coupling. So, this is the path B is here, you can see this radical anion is generated, and in the path B process it reacts with another radical anion. So, it is actually dimerization, and then you get this Pinacol O samarium compound, and after proton source you get the Pinacol products. Alternatively, in path A you can see this radical again can be converted to anion that we have seen earlier also with samarium iodide, and then you get this anion. So, this is anion is forming here, carb anion is forming, and then it is reacting with carbonyl compound to generate the same intermediate. And this radical also again can react with a carbonyl compound. Then you can generate this O dot here, and this O dot, these are very less common, and with samarium iodide you get this O dot becomes O minus, and after proton source you get this Pinacol. So, there are 3 mechanisms possible. Now, we will see intermolecular Pinacol couplings. So, in the intermolecular coupling cases, if it is bulky aldehyde, so this is pivalaldehyde. So, tertiary butyl group is present, and with samarium iodide THF room temperature only you get these 2 products in 8.5:1 ratio. This is the trio product and this is erythro, and you get this product in 79% yield. So, for bulky aldehydes, high diester selectivity can be obtained, like here 8.5:1. Now, if simple benzaldehyde is there, this reaction it has been found that with samarium iodide if you add tetraglyme, then the diester selectivity can be improved. So, in this case of course, the opposite erythro is forming as measured 5.9:1. So, without tetraglyme the diester selectivity is poor. And this is the structure of tetraglyme. So, there are 5 oxygen atoms are present. This is the structure of tetraglyme. This of course coordinate with samarium. Also this one, this is not so bulky, like alpha methyl butyraldehyde with samarium iodide THF and tetraglyme, you get this product, trio product in high diester selectivity 10:1. So, this erythro is formed here 1% minor, however, the yield of this reaction is low, 24% only, and this was published in ChemCom 1999. Now, we will see intramolecular Pinacol coupling. So, we have seen the intermolecular Pinacol coupling, the diester selectivity is less, but intramolecular cases we can see the diester selectivity sometimes is very high, because you can create the cyclic transition state. Like here, this compound you can see aldehyde is there, ketone is there, and 3 O benzyl groups are there, and with samarium iodide THF tert-butanol, you get this product in 64% yield, and this is very highly diester selective. You can see this OH are newly generated hydroxy groups are seen, and with the bulky group this hydroxy is anti. And we can propose a transition state like this pseudo chair, that all O benzyl are in the pseudo equatorial position, and this is actually the radical anion. So, radical anion geometry. This radical anion O minus here, and this coordinates with the ketone. So, aldehyde will first reduce to the radical anion, and that radical anion it will bring 2 oxygen atoms in the same side, because samarium 3 will coordinate with both the oxygen atoms here, and you can get this kind of geometry, and that is why this scene selectivity is observed, and this was published in Tetrahedron 1997. Also you can see this O benzyl and this OH are in the anti. Also, if you have a ester groups, this ester, it is interesting that when this carbonyl wants to coordinate with this aldehyde via samarium, then this CO2 ET does not coordinate, because this interaction is less important here, samarium samarium. Here the important is this and this, because here the radical anion will form and that wants to coordinate with the ketone. That is why these two hydroxy groups are the syn, and this ester group is actually anti, because this is the more bulky here compared to methyl. So, this is anti and these two hydroxy groups are in the syn. This was published in JOC 1988. Also, you can see this aldehyde and ketone is present, also Evans auxiliary is present. This is Evans auxiliary oxazolidinone. So, this is a chiral compound. With samarium iodide condition, THF tertiary butanol 52% yield of this product. So, here also the chiral product is formed in highly diastereoselective fashion. These two OH are in the syn and this hydroxy and this group is anti. They are in the anti orientation. And this was published in JACS 1989. Now, these pinnacle couplings can be extended to imines also and their equivalents, and in particular oximes and hydrogens, because we know different imines are available, but oximes and hydrogens they are less electron deficient. So, if they are neutral, have proven their worth in heteropinnacle cyclization reaction and have been used in the construction of 5 to 7 membered carbo and heterocycles. So, generally the intramolecular is favorable. So, intramolecular with high diastereoselectivity can be obtained. So, this is intramolecular and this carbonyl and this imine you can see here, and this is obtained also in high diastereoselectivity, measured diastereomeric 7:1, and samarium iodide THA minus 78 degree centigrade to room temperature you get 75% yield of this product. And also you can see this NH-OH bond here, that also clipped. So, this bond is clipped. So, you get the free amine here. First the nitroso is getting reduced with the samarium iodide, and this then coordinates with the carbonyl compound, like earlier we have seen the radical anion coordinates with the carbonyl, and that is why this syn selectivity is observed. Also intermolecular also is possible. This is a cyclic N oxide, and it reacts with benzophenone, and this compound is very important, alpha alpha diphenyl pyrrolidine methanol, and this compound is obtained with samarium iodide THF water. Here water is added, minus 78 degree centigrade to room temperature you get 83% yield. So, water enhances the reactivity of samarium iodide, and here also the similar mechanism is operating, that here the reduction is happening first and then this radical can react here, and then second samarium iodide will convert the radical to the O anion, and you get after proton source you get this. This was published in Angiochemy International Edition 2002, page number is 1772. Now, we will discuss another important reaction, carbonyl alkene coupling. This is also very important reaction. So, carbonyl group reduction we have seen, then we have carbonyl dimerization we have seen, and now we will discuss that carbonyl, whether it can be reacted with electron deficient olefins and whether CC bond formation is possible. So, carbonyl alkene couplings represent one of the most widely studied and most useful carbon-carbon bond forming reactions promoted by samarium iodide. An extensive array of coupling partners has been investigated in a remarkable range of intramolecular and intermolecular reactions. Fundamentally, the reaction can be considered as a highly efficient method for the reductive coupling of aldehydes or ketones to alkenes, alkynes and aromatic systems with moderate to high diastole control. Mechanistically, these reactions have been described as ketyl alkene couplings involving single electron reduction of the carbonyl substrate to give a ketyl radical anion intermediate followed by addition to the unsaturated carbon-carbon bond. Subsequent reduction of the new radical intermediate leads to samarium-3 enolate or enolate type species, which abstract a proton from an acidic source. Here two kinds of mechanism is possible, that in one case we can think that the carbonyl group is first reduced, and another case it is possible that the electron deficient olefin is reduced. So, in the traditional mechanism the carbonyl is first. So, carbonyl first means this is the carbonyl compound with samarium iodide, it generates this radical anion, and then this radical anion reacts to the electron deficient olefin, because Y is electron withdrawing group, and then this C bond is forming. So, this is C bond formation. And now this radical also will be stable by electron withdrawing group, can react with another equivalent of samarium iodide to generate the anion. So, here carbon anion is forming, and after proton source you get this OH become, and here also H, and this can be considered as Ampoulang reaction, because the carbonyl group there this anion is generating or radical is generating, and that is adding to the electron deficient olefin. Although this reaction mechanism has been accepted for many years, more recent evidence has shown that an alternative mechanism may also take place when electron deficient alkenes are involved. So, here this is the other way, here the olefin is first. The mechanism involves selective conjugate reduction of the double bond followed by anionic or possibly radical addition to the carbonyl group. Therefore, the precise mechanism for a given reductive carbonyl alkene coupling will depend on the specific combination of reactants and the respective rates of reduction of each component by the lanthanide reagent. So, here the alkene first is happening, same substrate electron deficient olefin samarium iodide, the reduction is happening, and you get this radical anion, this can stay like this or this, and this can react with the carbonyl compound to generate this. So, if the radical reacts, then you generate this, or the anion reacts, then the radical stays here. So, these two can form, and with samarium iodide again you get this O dot or C dot becomes anion. So, here this carbon anion is generated along with O anion. Alternatively, this radical anion can react with samarium to generate this dianion, which is less likely though. Dianion can react with the carbonyl compound to generate this, and this on proton source generate this neutral compound, which is the product. And we will discuss now this reaction intermolecular carbonyl alkene couplings examples. So, here it has been seen that if a hydroxy group is present, hydroxy always bonds with samarium, and whether this reaction can be done in highly diastereoselective fashion or not. So, here this radical anion is forming, radical anion, and if it binds with samarium, then this also will be same site of hydroxy. That is what we have seen, this hydroxy they are in the zigzag, and in the zigzag they are in the syn orientation. And when treated with alpha beta unsaturated A star, then this CC bond formation along with lactone formation, CC bond formation plus lactone formation is happening. This OH reacting to the A star to generate a lactone, and this product is formed in highly diastomeric ratio, Dr is equal to 99:1. So, these two OH group, this OH and this is the lactone CO bond, they are in the syn orientation, and these two methyls are also seen here, and this lactone is formed in high DR. This was published in JOC 1995. So, this is intermolecular. Now, intramolecular cases also, that we have already seen intramolecular phenol coupling. Similarly, intramolecular carbonyl alkene coupling can be also diester selective. Like here, if you have this ketone, here a double bond is present. Also, this double bond here, in this case, you do not need the electron deficient. So, no need of electron deficient olefin for intramolecular cases, because intramolecular are always fast. So, you do not need an electron deficient. Here simple olefin is enough to do this cyclization, and you can see this is a ketone, R is equal to methyl, R is equal to isopropyl, R is equal to tertiary butyl, R is equal to phenyl. You get moderate to good yields with this condition samaramidite THF, HMPA, tertiary butanol. But when you change this substituent, you get defined diester selectivity. So, this is OH and methyl, these are anti, and here OH and methyl, they are syn. So, in general the anti is more. When R is equal to methyl, then you get greater than 150:1, R is equal to isopropyl 23:1, R is equal to tertiary butyl, you get 3:1. So, it is getting reduced when it is the bulky increases, and R is equal to pH, you get completely reversed. So, in this case reversed. So, here 150% of syn is formed and 1% only trans is obtained. So, what could be the mechanism? So, this kind of transition structure might operate, that the 5-exocarbonyl alkene cyclization can be explained by invoking a chair like anti-transition state structure, in which the newly forming carbon radical center is eclipsed by the ketone substituent. So, here this O samarium takes this anti with this double bond. Increasing the size of the substituent disfavors the anti-transition structure, and the diester selectivity can be reversed. So, in this anti-transition state, you can see this is big of course compared to R. So, that is why we are calling anti. However, if R increases, then anti is less stable. Then this interaction also, because R is with this double bond, and syn case of course the syn transition state typically disfavored, because this is in the same side with O samarium. So, this will feel the steric interaction, and this favor R is big. So, when R is big, then this syn transition state is major, because that case this double bond wants to stay anti to the R group. And in this case, when R is equal to small, then double bond wants to stay anti with the O samarium. And this work was published in Anglo Chemistry International edition 1995, page number is 2383. Some more examples of intramolecular carbonyl alkene coupling. So, we have already told that this carbonyl alkene coupling intramolecular cases, you do not need the activated olefin. That is why the scope can be broad, and you can see here this is a 8-member ring, and carbonyl is there, the olefin is there with samaramidite, THF, HMPA, tert-butanol, you get this bicyclic compound product in 70% yield, and this is the reaction is happening. So, here this reacts here 1, 2, 3, 4, 5, and this case also 5, 5. So, 5, 5 bicyclic product is formed in 70% in, and highly diester selectivity. OH and methyl are in the syn. Here this kind of substrate we have seen that the carbonyl and amide is present. So, earlier we have seen that when there is a aldehyde, then the samarium iodide wants to coordinate with this, because this radical anion will form from the aldehyde and that will coordinate with the ketone. So, that cases we have seen the syn observation, and this was anti with the newly generated hydroxy component. Now, in this case the olefin cases we will see that they want to coordinate. So, these two are seen here. So, this is very interesting, because samarium does not bind with double bond, but instead coordinates with these two oxygen and they are in the syn, and this newly generated center methyl that we have already seen, this wants to stay anti. So, this is anti. With samarium iodide THF tertiary butanol minus 78 degrees centigrade, you get 78% of this product. And we can think mechanism like this. So, samarium 2 coordinates with both ketone and amide, and then this kind of radical anion transition state takes. So, this is the radical anion, you can see the carbonyl already reduced here, dot O minus samarium, and it takes syn orientation with this amide. So, they are syn, because they want to coordinate with samarium 3, and the olefin takes this kind of geometry. So, this olefin and O samarium, because here methyl group is there only, O samarium wants to stay anti, and after cyclization you get this geometry. So, this is very important. In pinnacle coupling we have seen the aldehyde and ketone are in the same side, but here if the aldehyde is replaced with olefin, then the ketone and amide are in the same side and the newly generated methyl will be anti. Now, we will discuss carbonyl arene coupling. In addition to alkenes, arenes can sometimes be used as radical acceptors in samarium iodide mediated carbonyl alkene couplings. We have already discussed, when we discussed chromium, that this chromium tricarbonyl arene complexes, they are electrophilic. So, electrophilic in nature, and this dot O minus, that dot can react here, and after samarium iodide again. So, this is 2 equivalent, you generate a anion here. So, most likely this will form methyl OH and this is the O methyl, and now after cyclization first a radical of course and then a negative charge will form C minus here, and this C minus, because this is unstable, this can take the H plus there and you can get anion there. So, hydrogen come here, anion goes there, and this anion, then the aromatization will happen. Aromatization minus OMe group. One OMe group will eliminate and you get this product. Here you can see one methoxy group is eliminated because of this aromatization. So, aromatization. This was published in Anglo Chemie International Edition 1995 2383. This is from Schmalz group from Germany. Also, this kind of indole system, here you can see ester motif is there, amide is there, ketone is there, and now if samarium iodide is added to the substrate in THF room temperature, you get first the reduction of the ketone of course, then the radical anion forms, and then the de-aromatization will happen, because this radical will add to here and another equivalent of samarium I2 will generate this enolate. So, this is ester enolate is formed. You can see this also in highly diastereoselective, this O samarium and this hydrogen is the same site, and now this enolate if you treat with allyl bromide, allylation will happen. So, this is allylation. So, this enolate can be treatment with allyl bromide Again this product is highly diastereoselective, highly diastereoselective, and this work was published in Organic Letters 2003, page number is 4305. And lastly, we will see reductive couplings of imines and their equivalents. The use of a nitron equivalent to a carbonyl alkene coupling also provides an alternative approach for asymmetric control through the attachment of a chiral auxiliary to the nitrogen of the nitron. So, here you can see this is the nitrile oxide, and when treatment with this is chiral of course, and this is pseudoephedrine is present here, and now this CC bond will form. So, this is the newly generated CC bond, and this newly generated CC bond is formed in highly diastereoselective fashion. So, that the cyclohexyl group is in the downside. So, this is downside, and the diastereomeric excess is 9:1. Under this condition, samarium iodide, tert-butanol, THA minus 78 degrees centigrade, you get 70% yield of this product. And this was also published in Organic Letters 2003, page number 229. And this is cyclic N oxide. This already we have seen similar, but here this is chiral. So, this is chiral. So, here the chiral olefin is chiral, here the N oxide is chiral, and when ethyl acrylate is treated with samarium iodide, water, THA minus 78 degrees centigrade, this newly generated CC bond is formed in diastereoselective fashion, and this is down. So, this is up. So, these two are trans. So, this is very important. Here these two are trans, here this and phenyl are in the trans, and this was published in JOC 2005. Radical alkyne additions, the addition of sp3 sp2 carbon center radicals to unsaturated carbon-carbon bonds is yet another class of synthetically useful reactions promoted by the low valent lanthanide reagent samarium iodide. So far we have discussed the carbonyl alkene reaction. Now, we will see the radical is adding to the olefin, that is also possible. Halides and sulfones are the most common functional groups used as precursors to radicals, although other groups have also been successfully employed. Although the intermolecular variant of this reaction has found only limited application, intramolecular variants can be highly successful. The use of samarium I2 has clear advantage over the use of tin hydride reagents to initiate radical cyclizations. First, lower reaction temperatures can be used in conjunction with samarium iodide as a thermally labile initiator is not required to generate the radical, that is when tributyl tin hydride is used. Here the initiator is not required. Second, the lanthanide salts generated after completion of the reaction are considerably less toxic than tin byproducts produced from tributyl tin hydride, and they can be easily separated from the desired cyclic products. So, this is the reaction that we know that if a halide is there, then samarium iodide generates this radical, and this radical of course with reduction it can generate this R samarium I2. Alternatively, if there is a double bond is present, then the radical cyclization will happen, that will generate a new radical, and that after quench this samarium iodide will generate this anion, and anion after proton source will generate the neutral compound, and X can be halide or sulfone. And this is mainly for intramolecular cases, because then this radical immediately reacts, and we will see some examples now. So, this is sulfone. So, as we have seen the intramolecular cases, so here mostly you can see the intramolecular, because the radical will immediately react with olefin, and this olefin is not electron deficient. So, simple olefins also can be used for intramolecular cases. So, sulfone here you generate the radical, and that the radical reacts here. So, you get this product with samarium iodide HMPA. And this kind of substrate is present, then this iodide, the radical will form, radical will add to this olefin and you get this product. So, here you can see they are trans. So, newly generate a chiral center is trans to the, and after chromic acid treatment we can get this lactone, butyrolactone in 98:2 ratio. Also if you have a sulfonyl like pyridine sulfonyl group and this kind of olefin is present, then also similar cyclization will happen. So, 1, 2, 3, 4, 5. So, 5 exotrig cyclization is happening, you get this samarium iodide HMP THF, and if you treat with TBAP, then these two bonds are cleaved. O silicon carbon silicon bond is cleaved and you get the free hydroxy group and this is the ethyl group. This product is obtained in 80% yield after 2 steps. And in cases that if you add nickel iodide as additive, then the reaction is very fast. This has been found that if you radical alkene coupling, if you add nickel iodide catalytic amount, then the reaction efficient is very high. Of course, two kind of olefin is present. Of course, this is activated olefin. So, this is activated, and in this case the radical that is forming is adding to the activated olefin, and this olefin is untouched. This is untouched. However, the diester selectivity also here is very high. This is trans again, trans, and you get this diasteromer greater than 100:1. This case also you get this trans product in greater than 100:1, and this is the transition state. So, the radical will add to this. So, this is the CC bond formation is happening here, CC bond formation, and in this case there is no A13 stain, though it is here, but this is minor because hydrogen is minor. But in this case, if it is R is up, so R and newly generated bond is in the same side, then you can get this R hydrogen, and there you can get this allylic 1,3 stain. That is why this one is less stable. So, this is more stable, and this will give you trans product because R and this are in the opposite side. Some more examples, radical addition to alkenes, like here cyclohexanone system, X is equal to oxygen, X is equal to NMe, so lactone or lactam, then samarium iodide THF, tert-butanol, catalytic nickel iodide, you get this bicyclic compound. So, this radical is adding here. Also, if you have this kind of substrate, and here also this is the aromatic iodide, and with samarium iodide you get the aryl radical, and this radical immediately react in 5-exotrig fashion. So, this is not activated, and in this case you get this, and with samarium iodide HMPA you get the carbanion. So, this is carbanion. The electrophile can react with this carbanion and you get this kind of product. And lastly, we will discuss radical addition to alkynes. So, like this alkyne, this is the OBN, CH2Br is there, and OBN is untouched, and in this case 5-exo-dig reaction is happening. So, here radical is adding to the alkyne with samarium iodide HMP THF condition, you get 86% yield, and in this case also 5-exo-dig is happening. So, dot we generate 1, 2, 3, 4, 5. So, add and you get this exocyclic olefin, because this is amide here, and exo-dig is very favorable. Under this condition, you get this product in 90% yield. Now, we will discuss radical addition to amines. This is also possible, like here if you have a iodide bromide and if you have a hydrazone. So, this is hydrazone, then this kind of products can be obtained, and in this case they are seen. So, the seen products are formed major, that we will discuss why, and you can see Dr can be 7:1 when X is equal to Br, X is equal to iodide, you get high Dr. So, this is the mechanism, the transition state. Here if you put HR, then you get a interaction, and this is disfavored. On the other hand, if you put R here, so there might be some interaction with the nitrogen, but this group is far. So, this interaction is minimum, or interaction is minor here, this interaction. That is why this hydrogen interaction is also minimum. So, that is why this is favored, and that means this nitrogen and this R will be in the syn for the imine cases. So, today we have discussed samarium iodide mediated reaction. First we have discussed the alpha bromo ketones, amide, as well as the ester reactions, and in this case we have seen that the alpha substance can be removed, and then we have seen if it is alpha chloro beta hydroxy esters amides are there, then the alpha beta unsaturated esters or amides can be produced. And then we have seen the nitro group reduction. We have seen that the nitro group can go to the 4 equivalent, it can go to the hydroxylamine, and with 6 equivalent it can go to the amine. And then we have discussed different CC bond formation reactions. We have seen the pinnacle coupling cases. We have seen the carbonyl group can react with another carbonyl compound, and in this case you can get high diastro selectivity for the bulky aldehyde like phenylaldehyde, and other case you have to add some additive. Then this additive can increase the like tetraglide, this additive can give the high diastro selectivity. Then we have seen the carbonyl alkene coupling, and this carbonyl alkene coupling we have seen that the both operation is possible, that the carbonyl first as well as the alkene first, and we have seen this carbonyl alkene coupling, the reaction can occur in high diastereoselective fashion, and depending on the substituent R, generally the antiproduct is forming, but if R is equal to phenyl, we have seen the syn product is measured. So, highly diastereoselective way you can get this product, and then we have seen the lastly radical alkene, and this is mainly the intramolecular cases. Also in these cases, intramolecular cases, the olefin can be normal, that is no electron withdrawing group is required, and in this case also we have seen the highly diastereoselective way you can get this product. Generally you get the trans product, because the allylic strength in the transition state will be minimum. And for the imine alkene cases, we have seen that the syn product is measured, because here also the interaction will be minimum when it takes the syn orientation we have seen. And in the pinnacle coupling cases, we have seen that the intramolecular cases also you can get high diastereoselectivity. Thank you.